It's good to be talking, and thanks for getting the core principles track. I mean, we're really excited to talk about this. So what we'll do is we've also scaled this presentation. So we'll start really from the very basics. And as we progress, we'll cover deeper problems that we've faced, and we'll talk about learnings as such. There are lots of things that we've done. There are lots to be done. So we'll talk about some of our experiences and what we've done to solve some of the problems we've faced operating Elasticsearch for PayPal. Okay, from an agenda perspective, before we begin, can we do a show of hands on how many people here have used Elasticsearch? Okay, quite a few. Okay, and how many of you have experience managing Elasticsearch? Okay, 1, 2. Okay, not quite. Thank you. So what we'll do is we'll do a quick introduction of what we do at PayPal, and then we'll start this by talking about what our team does, what search means at PayPal, and then we'll slowly start basics for people who are not initiated into Elasticsearch. We'll talk a little bit, basic terms about things that you got to know so you appreciate the content that's going to come at a later point. And then we'll talk about what it means for scaling Elasticsearch. I mean, what does it really mean when you say scaling Elasticsearch, right? And when you have a scaled cluster, what does it actually mean to manage a cluster at scale, right? We'll also go through a quick demo. This demo is, a shorter, scaled-down version of a problem that folks who've managed Elasticsearch at production would have seen. It's a scenario where something happens and the cluster dies. You just have to bring back the cluster. What do you do and what can you put in place proactively to make sure these instances don't happen? So we'll do a demo, quick demo of that, and then we'll take questions that you might have. Okay. So introductions. My name is Vikram. I have Aishwarya with me. We both are part of the technology platforms and infrastructure team at PayPal. So this team builds horizontal platforms and services that are used by all other teams and customers within PayPal. So we build the horizontal services like the search platform, anything that's got to do with notifications, all of those horizontal services that are in need for other business teams. So business teams could actually focus on doing their part, so they don't have to deal with managing the infrastructure, dealing with scalability, availability problems, etc. So that's what we do at PayPal. I have over 15 years of experience on dealing with large-scale distributed systems. I'm a big data enthusiast as well, so I've worked on Druid, started on Elasticsearch. Aishwarya here has extensive experience managing Elasticsearch, so she does, her day job is to make sure all our Elastic clusters kind of stay up to date, serve the business needs that we have at PayPal for Elasticsearch. Quick overview of search platform. We call this a search platform for a couple of reasons. One of the reasons is in a scale like PayPal, it is very important for us to decouple the complexities of managing infrastructure, providing software as a service to people, and not have teams take care of setting up Elasticsearch or any other software for that matter. So one of the things we do as a platform is to basically provide a fully managed search infrastructure for PayPal. So what we do is take care of provisioning the clusters, managing the cluster, making sure they operate, making sure they are scaled as per the customer needs. And also we have an abstraction layer in the middle that lets us swap out any other search infrastructure. So tomorrow if you want to move from Elasticsearch, say for example Solar, or you want to provide something like Search on Hadoop, for example, for use cases that do not require sub-second latency, we could do that without customers being directly impacted. So we have that layer as well. But the focus of this talk is just going to be specific to what we've done with Elasticsearch, right? To talk about scale, we manage about 1,500 plus nodes, and we are growing phenomenally over the last couple of years. This accounts to about 4+ petabytes of data across multiple clusters. So these are not just single cluster with those many nodes. We have multiple different clusters that have this data. We have about 20 billion ingests a day, just to give an idea of what scale means to us, with a 50+ million searches a day, right? We also have some other offerings marked out here. Sorry. Okay, we have a custom security plugin and a custom monitoring and alerting plugin. So for folks who've not been following Elasticsearch, uh, very recently Elasticsearch just open sourced their entire security stack post Amazon releasing their open distro for Elasticsearch. But this was something that we did way back because PayPal being a company that deals with a lot of data that's secure, we need to make sure there are certain clusters that need to be protected. So the existing paid versions of what Elasticsearch provides did not quite work for us, both in terms of cost and the features that we needed. So we had to build something on our own for that. And then we also had to build some custom monitoring and alerting solution that plugs into the overall PayPal's ecosystem. So what Elasticsearch and the ecosystem provides kind of works, but it's a little difficult to integrate into your existing monitoring and alerting systems. So we built our own. So those are offerings that we provide as part of search platform within PayPal. Moving on. We'll talk a little bit more about Elasticsearch. I think there are a lot of people who know about Elasticsearch, so we'll breeze through these slides really quick. So Elasticsearch is an open source software released in 2010, available under Apache license. It's based out of Lucene, which is a really powerful search and analytics engine. It's distributed in the terms that the data is distributed across clusters. It's horizontally scalable, also provides a lot of resiliency features. It's schema-free. All documents are JSON formatted documents. Elasticsearch does its best to infer types automatically, but it also lets you the ability to give it an explanation of what the data means. And everything is done via RESTful API. So pretty much everything in terms of ingesting data, searching for data, managing clusters, everything can just be done by firing HTTP queries, JSON-based HTTP queries. Let's talk about some of the use cases for which people very widely use Elasticsearch for. Of course, the structured, unstructured sources. So things like faceted navigation, pagination, full text searches. These are really the areas of focus for Elasticsearch, Solar, and Lucene in particular. You can also do fuzzy searches, so things like did you mean? So you are on a website and you're trying to search for something. So for example, a classic PayPal use case, you're trying to look at your account activity and you have a bunch of transactions done over a period of time. You're searching for a particular user. You just misspelled the merchant's name or a customer's name. This would actually tell you, did you actually mean this? We see this in multiple other websites as well, so that's something that's a forte for Elasticsearch too. Another thing is aggregation, so things like doing bucketing. So if you want to do things like group by, those are really insightful for the data that we capture within Elasticsearch as well. And on top of this, Elasticsearch also comes with powerful visualization. So Kibana, which is one of the software that comes bundled with the Elastic Stack, and you also have Grafana that I think many of you would have already used. They come with really good integrations with Elastic. So this gives you, near real-time actionable insights. So if you collect data across your system, make sure that data is available in Elastic, you can actually build really powerful graphs that tell you the state of the system. Before we move on to what's in it for SREs, we'll also cover some use cases on what PayPal uses Elasticsearch for, just to give you a brief overview. So there are two different things we use Elasticsearch in PayPal for. A couple of things are customer-facing use cases, like the example that I mentioned where you have activity search, for example, or a customer is trying to find out a certain way to do a thing, and they go to the PayPal's help center page and they want to search something, they can do that. Or you can we also use Elasticsearch to do geospatial search. So if you're trying to find out a store that accepts maybe funds in for PayPal, you could actually go to your PayPal app and then do a location-based search, so to find out all stores close by that could give you. We use Elasticsearch for that as well. So that's the customer-facing side of it. Elasticsearch is also heavily used on the systems and SRE side of it. So we use that to do payments monitoring, very critical payments monitoring, so it keeps track of all the business metrics. We also do a lot of analytics around logs and error rates, and our developer integration platform uses Elasticsearch extensively. So when people actually onboard onto Elasticsearch, we have a sandbox environment for developers where people actually come and try this out. So we monitor all the errors and things like that, so we can proactively reach out to people, solve their problems. So that's also something that we do based out of Elasticsearch. Moving on, we want to give a little bit more about why is Elastic so famous in the SRE community. Like off late, it's actually used by a lot of different companies and teams. One of the things is actually in our effort to build observable systems, there is a need for us to make sure that we collect all our telemetry in a single place. That also gives us the ability to do things at scale. So think about collecting all your logs and errors and your matrices and things like that across all your ecosystem of microservices, getting into a place, building dashboards. That's something that you could do really easily with Elasticsearch. And it also comes out with tools that could provide you real-time actionable insight. So like I said, it comes bundled with Kibana, and the learning curve for a person who wants to use Elasticsearch is really small. So if you just understand the basic and you get the ecosystem provides a lot of pieces that lets you easily get all your telemetry data into Elasticsearch and build visualizations really easily. So that's another thing which the SRE community might appreciate. Before we actually go on to what it means for scale, there are certain things that you need to really understand in terms of terminology. So these are terms that will come later in the talk, and I just want to make sure that we mention that. So Elasticsearch, like I said, is distributed. So we have a concept of cluster. A cluster is nothing but a group of nodes that share the same name. So like I said, Elasticsearch is horizontally scalable. So you could spin up multiple instances over multiple instances, and they will automatically form a network. The only thing that binds them together is what we call the cluster name. So you say cluster.name is test, and you could spin up multiple Elasticsearch instances with that, and that would automatically form a 5-node, 3-node, or whatever that you're trying to spin. A node is nothing but an elastic process. So think of it as a JVM process that runs the Elastic with a bunch of configuration. There's little more to it. Elasticsearch also has different node types. So we have, since it actually runs in a distributed environment, there's a concept of a master node that orchestrates the entire cluster. So because it's resilient as well and it needs to distribute data, the master does the heavy lifting of making sure that the cluster is stable, there's enough cluster state maintenance and all of that. And then there's also a concept of data node. So master and data is something that you need to remember. So data nodes basically persist data and also help you search through data. Then we move on to something called a document. A document is nothing but a JSON structure. You can put in anything in there. It also supports nested objects. Elasticsearch, like I said, will infer types for it. You don't have to explicitly say, hey, this log line, consider this as a string, and this is the timestamp, consider this. Elastic will automatically infer it. While for production use cases, you might want to define this before you start ingesting data. So you can make a little more sense of what you ingest. An index is nothing but a collection of documents. So think of index, like in older versions of Elasticsearch, this might be equivalent to a database in the traditional RDBMS terms. In the newer version of Elastic, think of it like a table, right? We want to field is nothing but a column. So it's just maybe if you have log line stored, your error status, your timestamp, and these might be fields in there. You have mapping. Mapping is nothing but a schema. So if you go back to, again, your database, the schema definition for a table is what will be equivalent to what we call as a mapping in Elasticsearch. So this defines what all columns, what all fields are there, what are the data types of each of those fields. And we'll talk about something in the upcoming slide. So in terms of how Elasticsearch will interpret this data, right? Shards, like I said, Elasticsearch distributes data across the cluster. So shard is the lowest level of storage. So think of this as the lowest level in which Elasticsearch stores its data in a form that it makes blazing fast searches possible. Another thing you should be aware is something that we call the routing. At production scale, this is something that will really come in handy. So like I said, you can pump in huge volumes of data into Elasticsearch, and that will distribute this across the cluster evenly. The way it does it is by something that we call the routing. There are different kinds of routing. If you don't, so by default, Elasticsearch routes every document by what we call the document ID. Document ID is something that you can explicitly provide, or if you don't provide, Elasticsearch auto-generates one for you, and it routes the document to an appropriate instance of an Elasticsearch based on that ID. So it actually does a hash on the ID, and then it sends to that particular node. So that way, your data is split across the cluster in a uniform manner. So any time when you search for something, the load is distributed across it. That's why it makes it a little faster. There is also another way to route it is by explicitly telling it. Say, for example, instead of letting Elastic determine its own routing based on an ID, you can actually tell it to route it based on some construct that you have in your application. So for example, I want to make sure all my shards are split by account numbers. So you could do that. You could tell Elasticsearch to say that, hey, hash by account number. So the benefit of that is if you want to search for a particular account number, it always goes to a single shard, right? So you don't have to work across the board. So that works really faster. And Elasticsearch, before we talk about scale, Elasticsearch support exhaustive set of configurations that you can tweak. So one of the complexities of making sure you operate and manage Elasticsearch at scale is to make sure you understand all the trade-offs. So there are multiple parameters that you can tune, and how you tune a particular parameters, there's no right or wrong way to do that. The way you do that is basically dependent on the kind of use case that you want. So routing is a classic example of that, right? So you can either let Elastic do its thing, but when you're working at scale, sometimes it might not, be the expected behavior. So you might want to understand the use case and then determine your trade-offs based on that. Let's quickly look at some other terms and then just pictorially. So this is a sample use case. You have a 3-node cluster. So the individual boxes, consider them as elastic nodes. Like we said, the data is divided into shards. So each of those nodes have a certain set of shards. So the green boxes are what we call the primary shards, which is the first place where the data gets written. The gray boxes are replica shards. So this is to make sure Elasticsearch is resilient. So say, for example, in a case where you run this cluster and a node goes down, you won't have loss of data. The data that was available in that node would have been automatically replicated in another node. And the master node in Elasticsearch is keeping track of that. So the moment it realizes that, hey, a node went down, it will automatically route all the requests for that particular shard to the machine which hosts the replica. And it will also automatically kick off a process that makes sure another replica is created. So it always makes sure that there are enough copies of data to serve all your requests, right? We'll quickly go through how a indexing request works. So indexing akin to writing. If you have a document and you want to store that into Elasticsearch, how does it happen? So you have a JSON document, and you actually pick any node. Any node in Elasticsearch can work as an indexing node, so you can actually send the data. What it does is, again, tries to route it. It looks inside the data to figure out if there's a concept of ID. If there is no ID, it auto-generates an ID, hashes the auto-generated ID depending on the number of nodes and primary shards that you have set up, and routes that request to that particular node. So the node gets that request, stores that data, and it also figures out another replica where it can actually send depending on the cluster set. So it also looks at how loaded all your nodes are in the cluster, and it picks out the next least loaded node and sends the replica to be placed there. So it creates both the primary and the replica, acknowledges this back to the client, and one of the records is persisted now, unavailable for search. We'll drill this a little more deeper in terms of how this exact indexing works by taking up an example document. So here you have 2 documents. The quick brown fox jumped over the lazy dog, and another document that says the 2 lazy dogs were slower than the less lazy dog. So Elasticsearch, like I said, it applies a little more logic before it persists the document in the cluster. The first thing it actually does something called HTML strip. It removes all the HTML characters, so you had some EM tags over there that were removed. Then it actually does a standard tokenizer. So standard tokenizer just splits it by whitespace character, generates tokens of words. Applies a lowercase filter. So this is just to make sure that we do a case insensitive search. So if you are searching for an uppercase quick and you had a lowercase quick, the document is still found. So it stores everything in lowercase. And then it removes stop words. So you can define what the stop words are. If you don't provide them, there are default English stop words that are used. Those stop words are not indexed. So the output of this is what is persisted by creating what we called an inverted index. So the way it makes it faster is by actually mapping these 2 documents. So each of those individual terms are now converted into an inverted index. So the table that you're seeing there, in actuality, it's a little more complicated, but this is just give an idea of how it persists. So In actual, Elasticsearch stores a bit more details on the inverted index, but this is just give an idea of how searches are faster. So you have each term, and for each of those terms, you have a document matched to it. So, quick is it present in document 1, lazy is present in both document 1 and document 2, dog is present in both document 1 and document 2. So anytime you're searching for it, all it needs to do is just come back to this inverted index, look it up, figure out how many documents are there, figure out where those documents are there, and get you back the results. So that's what kind of makes it faster. So now coming back, now we have a document that's ingested. Now we want to move on to a search request. So somebody is wanting to search for it. So again, any node in Elasticsearch cluster can act as a node that can coordinate your search. You can send your search request to any node. So the first thing it basically does is it figures out sends the search request to all the shards that basically have the data. It can either pick up a primary shard or a replica shard. That depends upon the cluster state as well, right? And each of those shards individually execute those queries. So whatever search term that you were firing, that will be executed against that shard. If a shard returns that data is, so it kind of operates on a scatter-gather model. So it scatters all the query across the cluster, gathers all the results, sorts it based on the relevance criteria that you were provided during search, and returns it back to the user, right? We'll see that with an example. So taking the example of the same index record that we had earlier. So we had indexed 2 documents, and from that document, we're trying to search for the term, the quick brown dog. I'm not sure if you're able to look at the case in there. So the brown is capitalized, the dog is capitalized as well. What Elasticsearch will do is actually apply the same set of filters that it applied when it indexed the document. So it'll do an HTML strip, it'll do a standard tokenizer, it'll lowercase them, it'll remove stop words, and then use these 3 tokens and go back to the inverted index. So when it goes back to the inverted index, it says that, hey, quick matches 1 document, brown matches 1 document, dog is part of both these documents, and it'll send those 2 documents back to the client. Now, like I said, there are multiple other details that are part of the inverted index. You could also have something called the frequency, the position. So based on that, your records get relevanced better, right? So this is kind of how a search request would look like. Coming back from an installation perspective, like I said, it's really simple and easy to install Elasticsearch. All you just do is, get the binary, untar it, execute, and you have a cluster ready. You don't have to do any other configuration changes. While this is just an example of how a cluster is set up, this is not the way we would set things up in life. And how would you? This is just to show you the example of how easy is this to this is all based on REST API. So you just fire a request once you've started the cluster, and it tells you the status of the cluster, right? So this is how you would have a sample cluster up and running. You now have the basic terminology. Now the question back to this group is that, okay, you have a 1-node cluster now. Now what does it actually mean to scale this up to production scale? So I would like to hand it off to Aishwarya to talk about what challenges happen during scaling and how we handle some of those, and what it means to manage a cluster that we've scaled.
Thanks, Vikram, for that amazing, am I audible? The mic working? Okay. I guess it's working, yeah, thank you. Thanks, Vikram, for that amazing overview and along with the pictorial representations of how Elasticsearch works. Now, let's get into the details of scaling Elasticsearch. So what does scalability actually mean to us? We can simply put it, say, hey, you want to handle more workload for a given system. It can either be in the form of a functional scalability where you need to add additional features to your application, or it could be in the form of load where you should process more data and things like that. So that is about scalability. And how do you go about scaling an application? Say, for example, you want to expand your family, not in terms of kids, but maybe just by supporting another family or things like that. In that case, you can either have an additional room constructed in your existing place or a top floor, or you can, say, for example, you are in an apartment, you have no other go, you go and buy a different apartment altogether. So constructing a top floor or adding a new room, scale up, and then buying a new apartment altogether, scale out. So these are the 2 common ways by which any application is scaled for a distributed system. And how does Elasticsearch go about with it, or what does it mean for scaling in Elasticsearch? We'll put it in 3 different dimensions. One would be the ingestion, another one is in terms of search, and another one in terms of data volume. Ingestion, so I want to handle these many millions of records per minute, and maybe I would want to do it in a shorter period of time or handle more records for a given period of time. With respect to search, handle more concurrent queries or reduce my latency. In terms of data volume, I just come back and say, hey, I want to have additional data in my cluster. Say currently it's for a year. I want to do it for like 3 years. How to go about with it? So any Elasticsearch use cases that you have, you should have faced any of these 3 things or problems with respect to this. And very common problems, like once you started scaling, from how Vikram was telling, is very simple to set up a 3-node cluster in your QA or in your local environment. But once you productionalize it, you would have faced any of these 4 things for sure. You would have landed into either memory, CPU, IO issues, or you would have landed into the suboptimal queries, which is a very common problem. And there could have been some mapping explosion, or it could be the improper short configurations that you have given. Let's go into the details of each of these to figure out how we handled these use cases at PayPal. So that gives us a very serious question on, is Elasticsearch truly elastic if we are facing all these problems? Yes, it is if you tweak the configurations out of the defaults which is given. So if you plan to just productionalize it with whatever defaults that they have given, I am not sure if this statement would hold good. So let's start with problem 1. So say, for example, we start with ingestion. So you have a low ingestion throughput. You need to handle, say, 7 million per minute, which was a kind of similar problem that we had. And but the current process is around 5 million per minute or so. So you need to scale up for the additional 2 million. And how do you go about with it? There are several ways by which you can do. You can always add more nodes to it, additional resources and things like that. But how do you do it with an existing infrastructure is something that we have to think about. And that gave us 4 interesting learnings, which we would like to talk now. And these 4 proved out to be really useful compared to the remaining set of things that we tried out. To start with, it's the routing for bulk requests. So for bulk requests by itself is like an added advantage for any data store where you ingest data in the form of bulk documents and not just a single request. So that reduces the computational overhead of all that Vikram was telling, the analyzing part, indexing part, and all of it. So you always prefer bulk request. How about a combination of routing plus bulk requests? So routing is where you exactly go for a given request, you know which exact shard that it needs to go to. When you combine a routing field for a given bulk request, say this 100 documents will go to this particular shard in a given node. And then you have multiple parallel worker threads doing the same. In that case, all the nodes present in all the shards in a given cluster would start to maximize their throughput, and that is the first point that we did. Combining routing with the bulk request is something that helped us maximize the throughput. The second one is in terms of refresh interval. So you guys are aware of refresh interval by any chance? Like what it does or tried playing around with it? Okay. So since it's a silence, I'm taking, let me just go through that a bit. So
how quickly your metrics will push to the Elasticsearch?
Awesome. Something on those lines, how quickly it's available to search, exactly. So what it does is once you index a document into Elasticsearch, it has an in-memory buffer, and then it flushes into your segments, after which it becomes searchable. Once the flush happens, that is what you call as a refresh. And when you do this, Elastic spends some operation in the background to merge your smaller segments into larger segments, and there is a considerable amount of work being done there. And what happens if you increase the searchability part? What if you say, less frequently I want to do my merges? In that case, you get additional resources in order to scale up your ingestion. You will be able to process more requests. So all this that we are talking about is in terms where if it's a few hundred or few thousand requests, all this doesn't matter. But at a scale where we talk in millions and billions, what we do, like how you were suggesting before. So that is when all this comes into play, where you increase your refresh interval. So the trade-off of that would be the document would not be immediately searchable for you. Once you ingest, you won't be able to search it depending on whatever configuration that you give. That is the downside of it, but for SREs, and especially if you look into log monitoring, I think a delay of 1 or 2 minutes is not a very big deal, which could be compromised for the throughput that you get. The third one is the number of shards and the total shards per node. As we say, shards is something that will help you to distribute the load and make your system more available. That also tells you how will you distribute your shards across your cluster. The default configuration is that you can have unlimited number of shards in a given node for a given index. So what if you are planning to, there is an active ingestion going on today's index, but all of them are present in a single node, and then that particular node would go into heap or memory pressures. In that case, you distribute it across multiple nodes. That will be multiple VMs by itself, which can scale up your ingestion. That is the third part. And the fourth part is about the translog durability async. Anyone aware of the translog concept? Who is used? Okay. Translog is something where it is again an on-disk thing that happens. So when there is an indexing request, it is again put into a memory where it is a write-ahead log file is called as a translog. And then the actual persistence to disk happens with the help of a losing commit. Losing commit by itself is an expensive operation. So what do we tell? Hey, do this in the form of, do these losing commits in an offline way. Do it async in the background way, where it doesn't happen for every indexing or search request, but it happens at a very, at a lesser frequency. So when we do this, they tremendously improved our ingestion throughput because it doesn't happen for every request. So those were the things that we covered as a part of the problem of low ingestion throughput, and that helped us to scale easily 10 million per minute. Moving on, so problem 2, node instability is due to mapping explosion and sparse fields. So mapping explosion, what does that even mean? For a given index, you have too many number of columns. When do you think things like this can happen? Where you don't have a proper orchestration and instrumentation on how do you go about defining your fields, or what is the values that I would put into a given cluster. And the second one is the sparse fields. So as you could see in the depiction of the diagram, where you have the few fields, but not all of them have values associated to it. In this case, it is the sparse fields, there is something called as a doc value, which is an on-disk data structure that is being built, which is done in a columnar fashion. Let's not get into too much of details about it, but in the earlier versions of Lucene, it has to spend some amount of disk space to even hold these empty values. Though in the latest versions, they have improved it in versions greater than 6x, it's always better to have a dense values. But there are problems. So when you talk about multiple applications pumping data into Elasticsearch, there are cases where you can land into an issue of mapping explosion and sparse fields. And what were our learnings out of it? So the first thing, always keep a watch on the mapping. So mapping is something that you have to take care before even you design your application. You would have to put absolutely mandatory fields only, and even at a later point of time, you have defined a mapping, but if you want to add it, you need to take care of what you add. Second thing, split indices. The initial problem that I was talking about, mapping explosion, where you will have too many fields, if you are able to logically group your data in such a way that they are put into multiple indices, the problem of mapping explosion or the sparse fields would never come. So that is some sort of grouping that we could do. In our case, like it was the payments monitoring, where we had multiple payments app publishing data to an index, and they had some random fields being populated every day, and that created problems. So what we did, put all of the payment pools in different indices, and we had a common prefix for all of the indices in such a way that in Kibana, if you search for it, it's still available with no impact to the customer. And another best practice is what we would say, go for date-based indices any day. So if you want to change any mapping, you can always go ahead and then do it. That helped us with respect to the sparse fields. Because of splitting indices, we were able to reduce our 20% disk space, and our search latency also came down as it is very specific to an application. Then, problem 3, expensive or suboptimal queries. I think this is a very common problem across all data stores, and we can think this in two perspectives, where you manage your platform and then you act as a consumer for your data as well. In that case, you exactly know what you're going to fire against the cluster. The other case, like the state where we are in, we offer search as a service, a platform where multiple users can come and leverage the search service for something. If we put it specifically in terms of SRE, say for example, you have a data set and that is being used by all across PayPal, where they have a control of whatever query that they want to fire. That also poses a very important aspect of things where we need to look into the query governance. We'll have to know what is being fired to our Elasticsearch clusters. But on a real-time case, will you be able to figure out is a question mark, and we'll have to find our ways around on how do you deal with scenarios like that. So let me just walk you through a few common examples or things that people might do, which are potentially vulnerable queries. The first one, someone wants to do a group by based on an ID field. The Elasticsearch queries look something like, hey, I want to do a group by based on email ID, and then the result looks something like this. So what is the problem with this? Like, does anyone see any problem with this query? If you are aware of the concept of cardinality, so cardinality is the number of unique values that for a given field can have. So this email ID is a high cardinality field. Each field can have a value which is unique to it. Say, for example, country code. At the max, how many countries do we have? And that you go up to few hundreds or go even for a few thousands. But email IDs is not of the same case. And then when you plan to do a group by on the top of it, it is a high cardinality field. There is a potential threat to the availability of the cluster because there is too much of data brought into memory, which is a global ordinal data structure. So if you get into Elasticsearch internals, you would understand how a data structure is being built in order to perform this operation. So this by itself is a potential query that can bring down. Second, retrieve all documents from Elasticsearch cluster. Another common thing that people might want to do. They just want to query the documents which is over there. First thing that I would say, never do that, never encourage. Elasticsearch is not meant for this. Elasticsearch works best for searches or does for aggregations and things like that. But if you want to just get the data out of it, prefer any other data store and not Elastic. Assume that it has already happened, or you have a use case where you need to query a huge resultant, where you need to retrieve a huge resultant data set. In that case, they go ahead with something called as a scroll, which is the only way by which you would be able to paginate and then get the data out. But what is the problem with this? Scroll maintains a context within Elasticsearch that prevents the merge operations. And anything with respect to deep pagination helps you bring all the documents in memory, which is again a problem. So this is another such example of a expensive query. Problem 3. Multiple levels of aggregation. So people just want, so in Kibana, if you guys have used Kibana for any of your visualizations, so you give a date histogram and then you have a couple of filters, you have a couple of aggregations, do a group by on the top of it. And then this again by itself is a problem because each of the aggregations, you will not be sure what is the bucket category because it gets dynamically built based on your resultant data set. And for the level of aggregations, those many buckets would be created in Elasticsearch, which is again a problem. And finally, the wildcard or the regex-based queries. Say this is bad in any data store and not just Elastic, but it's more of people should know about this, where you give a leading wildcard. What happens? So Vikram was explaining about the inverted index, where you have a list of terms and then the documents associated to it. Assume that you are giving something starts with an asterisk. What does it do? It's like a full table scan. The entire inverted index gets scanned to figure out, hey, like this field value is present in which of the documents, which is again vulnerable, but that is what we do because we exactly don't know what happens and we just go to Kibana and then do this, which is again a problem. We'll have to see how do we overcome with scenarios like this. So these were a few common problems that I was suggesting in terms of example queries, and there are numerous other things which I can keep talking about for all the experiences that we had. So that gave us 3 learnings, 3 byproducts that I would say. One is a query logger, another one is a gatekeeper, and the third one is a query optimizer. And let's go in order. So query logging. So just a food for thought. From what is the etymology of log, or why do you think we are calling something called as a log? Any random clues? Sorry?
Plotting? Not exactly. Yeah, it's an interesting tidbit. Why don't you go ahead?
So basically, it started in 1600 somewhere, where it is used to, a chip log is just thrown out, the one that you see down in the down picture, the below picture, where you just throw a chip log to some, just like an anchor, and then that is used to measure the distance the ship has traveled for a given time speed, for a given time. That is especially measuring the speed of a ship with the help of a sand timer. So that's where it started, and then later they make these entries of how the speed of the ship in a logbook, and then later now what we do in logs is the recording of computer events or file events that we have. So that's where the logging thing came from. Getting back to the topic. So logging in Elasticsearch. So if you guys are aware of the slow log queries that Elasticsearch offers, so they offer you a configuration which you can enable in order to log all the queries that is being fired or above a threshold and things like that. You can still do that to figure out what are the list of queries that are being fired if you are not very sure of what is happening in the system to get the visibility. But one downside of that is that it logs you at a per shard level and not at a request level. So you will not know at the end of the day, you would have to do some processing on the top of it to figure out what does your request lifecycle look like, or what are the different kinds of requests that are being fired. So that's when we came up with our own distinct query logger, sort a custom logic which will strip out the values of a given query, sort the keys, and then essentially compute the hash of a given kind of query. And then anytime when a new query comes into the system, we immediately figure out what that is and then analyze the cost of it. So that starts with the query logger. The second one is a gatekeeper. So you have queries coming from Kibana, or you can have application queries, or you can have Grafana that is going to Elasticsearch directly. And you have different kinds of users, and not necessarily everyone should know about Elasticsearch or how Elasticsearch queries will come up. So, but if that is the case, that again poses the problem of how I was telling suboptimal or expensive queries. So what we did was to build a gatekeeper that will intercept every query before it is being fired to Elastic. So you would figure out the cost aspect of it, and if you know that it's a rogue query, you block it right there. So we have built a capability of something like a blacklist, whitelist mechanism with the help of a rule engine that helped us achieve this. So with this gatekeeper, we were able to proactively prevent multiple incidents in live. Initially, we had a downtime of closer to 10 plus hours for the payments monitoring system that we were talking about. So there were some continuous rogue queries fired, the cardinality, high cardinality field that was done. Aggregations, which brought the cluster down, and there were like continuous queries being fired. So by the time we perform some operations, it again goes down. So that was a complete state of mess, and that's when we built something like this. So currently we have a capability like you can give anything like, hey, for time range greater than 48 hours, block it. Or if you have a nested aggregations level greater than 10, just block it, depending on the cost aspect of things. The third one is the query optimizer that we would talk about. So people are aware of this Kibana UI where you configure, if you are using a daily date-based index pattern, you have something like here FPTA asterisk is the index name. So that will have a list of date-based indices under that. And then you also have a timestamp on the top where you get to choose what you want to do. If I translate this into an Elasticsearch query, msearch query, this is how it looks like. You have an index name asterisk, and then you have a range, you have a timestamp, greater than, less than, and then this is fired to Elastic. So what happens? The actual setup looks like this. From Kibana, you have a query fired. Since you have a wildcard asterisk over there, Elastic doesn't know where exactly the data lies. So it fires a query across all the indices that are being present for the given matching index pattern, and then figures out whether for a corresponding, say for example, you give some date, which is the last 15 minutes. Essentially, it can be present only in the June month's index. But since you are using an index pattern asterisk, it still fires your query across all the indices. So how did we go about with this is that we built in a query optimizer layer that would intelligently look into the timestamp of the query that you are firing and then route the query only to that particular index. So what happens, your rest of the indices, which are essentially translating to the shards and nodes, are not put under load, and then you can serve additional concurrent queries. And this is not just in terms of timestamp, but you can also do it with various other parameters. So consider this to be a query optimizer layer, which can do optimizations with respect to the however you want to reorder it or the kind of queries that you want to do and things like that. So that was our third learning, the third byproduct that we had for expensive or suboptimal queries. So this is just about, you can reduce, in this case, we reduce the number of indices. You can also reorder the queries in such a way that you bring down the scan margin, because of which our search latency came down by 25%, and we got a better availability. Problem number 4, the oversized shards. So we have been hearing about shards quite often. And why does it matter? Like why is shards so important is that, like we were telling, it helps you distribute the load. Like you have an index that is distributed across multiple nodes, ensuring high availability. And then when you do that, you might land into any of these problems as you see in the picture. Assume that this is your current state and Elastic defaults go with 5 shards for a given index at this point of time, even with the latest version. So it's 5 shards. And then you start populating data into it. Over a period of time, your data size grows. But what happens? You continue to have 5 shards in your index. So the size of each shard keeps growing and growing. So shard is internally a Lucene index which can at the max hold certain quantity of documents. In their best practices in Elasticsearch, if you look at, they would say 30 to 40 GB is the size that per shard can handle. But what happens as in when you start populating data or your data size grows, there are possibilities where your shard size can exceed more than 50 GB. And like there were cases with us where like unknowingly it went up to 120 GB. And we had several issues when there were search requests because it's a complete shard search that it got to do. The second kind of thing is the skewness in the value of the routing key. Say you are going to use routing key to route a particular kind of documents in a given shard. Due to the imbalance in the distribution of data, there is a possibility where your shard size can grow. And what are the learnings that we had out of it is that initially the first thing that we would say is to anticipate the future and assign shards accordingly. If you have a second case where there is a skewness based on the routing value, you can split that into a different cluster or into a different index. If prevention is always better than cure, but if it has already happened, you have nothing but you have to just re-index the data, and re-index by itself is a painful operation, but that is the solution that we have, and that's why you always need to look forward and then anticipate it right. So that was more about scaling Elasticsearch. So I covered 4 problems, which were the few common ones that you would have faced, and how did we go about handling it. Another major part is managing Elasticsearch. So how do we manage Elasticsearch as a platform for our customers, and what are the things that are associated with it? Due to the interest of time, I think let me give a very quick overview on these 3 topics: monitoring your clusters, securing your Elasticsearch clusters, and how do you go about upgrading it. So if your entire ecosystem depends on Elasticsearch for monitoring and your Elasticsearch is down, isn't that a disruption to your entire monitoring by itself? Like all your applications use Elasticsearch, and then that's down, and then what do? You unintentionally or intentionally disrupt the entire system. So how do you police the police? How will you ensure that your Elasticsearch is available? So let me just flick a quote from Peter Drucker, who says, if you can't measure it, you can't manage it. So what does it mean by what you need to measure in order to have a better availability for Elastic? So there is something called as a node stats API, which Elasticsearch itself offers, where you have to collect data in all these 5 dimensions is what we have learned over a period of time. You would need data with respect to index, shard, thread pool, JVM, OS, and process. So these dimensions would help you exactly correlate metrics in case of an issue, which would say, hey, my thread pool is like low, and that's why my queue size is growing, and maybe that is why my ingestion is having a problem at this point of time. Or if you have some information with respect to JVM, you exactly get to know which node is facing trouble, and then you can go ahead and then perform the needful actions on the top of it. So that is on the collection part. So now that you have collected the data, where do you store it, or how will you make sense out of it? So that's when we were trying multiple options like building an Elasticsearch plugin and things like that. But this is something that we found relatively better, where you use the beats infrastructure of Elastic by itself, where you have 2 kinds of beats in it, the metric beat and the file beat. Metric beat is something that captures the JVM and the node stats related information. The file beats is the one that lets you scan your GC logs, slow query logs, or even Elasticsearch logs to figure out the kind of exceptions. And that will be shipped to your monitoring cluster. And then what do? We do analysis on the top of it with the help of a Grafana. So Grafana has Elasticsearch connector, so you can, like, we also have a talk tomorrow that says that a dashboard is worth of 1,000 words. So you can just figure out, like, correlate metrics, like you see one going up and then figure out, hey, what's happening with that node, what are the issues, and that helps you on the analyze part of it. And finally, once you have figured out an issue, that's when the alerting part of things comes into play, where we have multiple alerts set up in the form of email, Slack, and other SMS integrations that we have. And finally, by this point of time, you would have some root cause identified, and then you would start acting upon it. So that is with respect to monitoring your clusters. The second thing that I would want to cover about is about securing your Elasticsearch clusters. So why do you think we need security? At what point of time will I have a use case to secure my Elasticsearch cluster? Say, for example, you are putting some PII information where you have your account number or email addresses, which is very much possible in a production environment. Do you want it to undergo compromising or tampering or spoofing, sniffing, anything of that sort? So that's when we have to have a end-to-end TLS or SSL for that matter, where even the internode communications are secure, and from your application to Elastic is also secure. That also forces an authentication and an authorization mechanism that we need to have in place. Like how Vikram was mentioning, Elasticsearch has open sourced their, initially it was a licensed one, which they called as a shield, and now XPack security. But still, the ones that got open source doesn't have the audit logging or any sort of third-party integrations that you would require for any production environment. So that was also one of the reasons why we went ahead and then had our own custom plugin. Like this happened quite a year before though, before they open source. But there are other open source plugins like SearchGuard, Read Rest Only, all of those open source softwares that would help you do the same with having certain features as the premium features. So we came up with something called as a guard plugin for our internal use cases through which we achieve security. And then upgrading Elasticsearch clusters. So if you look over a past maybe a year or so, Elastic has released multiple versions. So it started with like 2.4 to 5x was the big, one that was taking time. And from 5x, they have released their 7.0.0. And though they call it minor version upgrades, there are quite a lot of breaking changes involved. And if you manage a platform, you would get to know that every time you can't ask your customers to upgrade, or it has its own challenges. Let me just talk about two things over here. So one thing is you have to figure out whether your queries are backward compatible. Whenever you plan to upgrade your clusters, the latest one has a lot of good features that you need to try out, but always check if your queries are backward compatible. If it is not, that's a blocker. The second thing that you got to check is the mapping. Mapping is something with respect to, hey, earlier they called it analyze, now they call it text and keyword. So keep a watch on those two. And approaches is something that depends from the kind of use case that we have. We would prefer the second approach, which is reindex from remote for any kind of upgrades that you want to do with respect to Elasticsearch clusters. Now let's look into the demo part. Let me give a little bit of overview about what you will be seeing here. So everyone should be aware of the concept of correlation ID, I guess. So that is the one that would let you stitch multiple transactions together. In this case, it is just a sample. I have populated some sample data in our test environment. And let's see, correlation ID is the field that is having your high cardinality field, and then you have some form of an API that is being defined. So we had one of the users who wanted to figure out the retries happening in their API. So what they did, they went to the Kibana, they had a correlation aggregation based on a correlation ID. They figure out that, hey, for this particular correlation ID, I have 3 counts, which means that it would have retried for a given request. And then what they do, hey, I want to see it for a larger data set, that they give a very huge value. And then you would see what happens. So Elasticsearch times out, it tells you error in visualization, and then that would return you an internal server error. So what just happened was a aggregation on a high cardinality field that they tried to do. So there are like inspect elements in Elastic which you could just figure out to see like your request and the response time taken and all of it. So this is the error that we had, and moving forward. Currently, your heap was somewhere around 40, and then after this query, it went up to shook up to 93, and then the exact logs that you see in the Elasticsearch logs would be the out of memory Java heap space error. So this is this was one of our live use cases where we had a similar kind of incident in live where all your nodes were going OOM because of this kind of thing. So this is the use of the gatekeeper that we were talking about. So what do we do is that in the Kibana YML, you do something like where your Elasticsearch, it doesn't connect to Elasticsearch directly. You have a proxy application in between that does that. And we had a configuration which says that, hey, block this kind of things. So in this case, they give a correlation ID based on keyword, and then when they try to query it, we throw an error telling that, hey, this is blacklisted, and then you need to contact the respective team. So this is just a custom thing that we put up for the sake of demo purposes. But we could have something like this for the help of query governance, and we can exactly control what gets in and what, so any new query can be blocked or whitelisted based on mechanisms like this. So I pause here, and then I'll open up for Q&A.
Go on.
You might have time for one question. hear me. What's the best strategy for aging the data out?
For?
For purging data?
For purging data, so if it is data,
Have you been using ILL?
correct.
ILM?
ILM.
Yes.
No, for Elastic so far, like whatever we do is we have this date-based indices. So you have a date-based indices for in the cluster. So you delete it. So you say, hey, my retention is for 7 days. Post 7 days, it's delete by index. So there is also something called as a delete by query, which Elastic offers, where you just feed in a query and then delete the data for that matches a query. But when we do that in production for heavy use cases, we find that little expensive where there is a immediate spike in CPU and then load average. So we always prefer deleting the complete index instead of deleting partial data within an index. So what it does is that delete by itself is like the segments would still be there in Elastic and later it would be merged. So that is expensive. So we wouldn't recommend that approach. We would always say, hey, delete your complete index. Like group it in such a way that it's a separate index altogether and then delete it is what we would suggest.
Thank you very much.
Thank you.